Hello, welcome to STT 315 Recitation 5. Today we are going to go over some definitions and then some properties and then apply that to some problems. So first let's go over some definitions. So an experiment is an act or process of observation that leads to a single outcome that cannot be predicted with certainty. So in other words, the outcome would be unknown. The exact truth would be unknown. So that's why we're, experimenting. A sample point is the most basic outcome of an experiment. The sample space of an experiment is the collection of all its sample points. An event is a specific collection of sample points. Further, a simple event contains only a single sample point, while a compound event contains two or more sample points. When a sample space S is finite, and each of the outcomes of the random experiment is equally likely to occur, we define, that word should be define, the probability of an event A as, so we have the probability of event A equals the number of outcomes in event A, or the number of sample points in A, divided by the number of all possible outcomes, or the total number of sample points. So we do that if each outcome is equally likely to occur. So we can take the number of outcomes in A and divide it by all of the possible outcomes. All right, so some important notation and identities. So A union B is all outcomes in either A or B. So when we have a union, we have or. A intersect B is all outcomes in both A and B. So for intersection, think and. For union, think or. A complement is all outcomes in S, but not in A. And remember, S is our sample space. So A complement is all the outcomes in our sample space, but not in A. If A intersect B is the empty set, meaning there's no sample points in A intersect B, or A and B, we have mutually exclusive events or disjoint events. And it's important to keep in mind that the probability of any event is in between 0 and 1. It cannot be less than 0 or greater than 1. So we have the probability of A is greater than or equal to 0 or less than or equal to 1 for all events A. The probability of S, our sample space, equals 1. So if you add up all of the events within our sample space, we should get the probability of all of those events occurring would be 1. The probability of A complement equals 1 minus the probability of A. The probability of A union B equals the probability of A plus the probability of B minus the probability of A intersect B. If probability of A intersect B equals the probability of A times the probability of B, so let's say this, if probability of A intersect B equals probability of A times probability of B, then we say that A and B are independent. And please note that this is not the same as disjoint. So independent does not mean disjoint. So in this case, we get independence. The probability of A given B, or the conditional probability of A given B, equals the probability of A intersect B divided by the probability of B. And the probability of A intersect B equals, so if we're using conditional probabilities, we get the probability of A given B times the probability of B, which also equals the probability of B given A times the probability of A. So this is known as the general multiplication rule. And so in some situations, this is good to know because you may be given, these probabilities and need to find, the intersection of A and B, the probability of A intersect B. But in some situations, you may be given information to solve like this right-hand side of the equality. Okay, and then the probability of A given B equals the probability of B given A times the probability of A divided by the probability of B. So all of this may seem a little bit overwhelming at first, but as we work through some problems later, hopefully it'll start making more sense. All right, so often it is convenient to graphically display conditional probabilities into the following tree. So here we can have either event A occur or event A complement occur. So either A can occur or A does not occur. And so the probability of A occurring, so our exact points would be like our events, and then we can think of these lines as like our probabilities. So yeah, probability of A can lead us to A, and then yeah, probability of A complement down here. So let's just look at the top part of this tree. So from this point, we can either have event B occur or event B does not occur. So if event B occurs, this would be the probability of B given A because A had already occurred. And then down here, this would be the probability of B complement given A. And then this lower half, so if A did not occur, so if we have A complement, then to get B, we would have probability of B given AC or A complement. And then if B complement occurred, then we would have probability of B complement given A complement. So here we would have, which would be, sorry, I forgot to mention. So if we look back at the top, we would have, this would be A intersect B. So A occurs and B occurs. Here we would have A intersect B complement. So A occurs and B complement occurs. And notice I'm saying and we're dealing with an intersection. And then here we have A complement occurs and B occurs, or down here we have A complement occurs and B complement occurs. So this is something that will be helpful as you do problems to kind of keep in your mind this tree diagram. And here's also a helpful relationship. So the probability of, I wish there was a way to show this at the same time, the tree diagram, but okay, the probability of B equals the probability of B and A plus the probability of B and A complement. So, and then that should equal the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. So this brings us to Bayes' rule. So let's say we're given K mutually exclusive and exhaustive events, B1 through BK, such that the probability of B1 plus the probability of B2 all the way to probability BK equals 1. And an observed event A. Then we have the probability of BI given A equals the probability of BI intersect A divided by the probability of A. And that equals the probability of BI times the probability of A given BI divided by the probability of B1 times the probability of A given B1 plus the probability of B2 times the probability of A given B2 all the way to plus the probability of BK times the probability of A given BK. So if you notice that this kind of unpacking of the probabilities that we discussed earlier is used in Bayes' rule. And the key for Bayes' rule is that we need to be given K mutually exclusive and exhaustive events, B1 through BK. So it's important that we have mutually exclusive events. And we'll be using Bayes' rule in a few problems at the end of this recitation. So you'll, be able to see how this is done in application. All right, so that's a little overview of the properties and definitions that we'll be using. So now on to our questions. So an experiment results in one of the following sample points: E1, E2, E3, E4, and E5. So we first want to find the probability of E3. If the probability of E1 equals 0.1, the probability of E2 equals 0.2, the probability of E4 equals 0.1, and the probability of E5 equals 0.1. So when I'm first trying to figure this out, the one property I'm going to keep in mind is that if I add all of the probabilities of the event of the probability of like E1 plus the probability of E2 all the way to E5, I know that should equal 1. And if I want to show you that rule, where is it? Yes, the probability here, the probability of our sample space should equal 1. And here our sample space is E1, E2, E3, E4, and E5. So here I have the probability of E1 plus the probability of E2 all the way to 5. So the summation of the probability of our EI equals 1. So that means if we add all of those together, we should get 1. And so now we can just plug and chug. So we're given the probability of E1 as 0.1, probability of E2 as 0.2. So I plugged in what we were given, and the only thing we were not given was the probability of E3. So I'm going to know that this equals 1, and then we're just going to solve for the probability of E3 algebraically. So 0.1 plus 0.2 plus 0.1 plus 0.1 is 0.5. So we'll have the probability of E3 plus 0.5 equal 1. And I'm going to close my window for a second. Hold on, sorry about that. There was noise. Anyways, okay, so then yeah, to solve, we're going to subtract 0.5 from each side, and then we'll get the probability of E3 equals 0.5. All right, so now we want to find E3 again, and we're given this information, so it's the same setup. We know that summing together all our probabilities of EI equal 1. So let's fill in what we know. So we know that the probability of E2 is 0.1, and E4 is 0.2, and E5 is 0.1. So I put in those numbers. And then we were given that the probability of E1 and the probability of E3 are equivalent. So I substituted the probability of E1 for probability of E3. So then that gives us 2 times the probability of E3 plus 0.4 equals 1. And then I'm going to subtract 0.4 from 1, and that'll give us 0.6. And then we want to divide by 2 on both sides. So in the end, we'll get the probability of E3 equals 0.3. Okay, next is find the probability of E3, given that E1, E2, the probability E4 and E5 is 0.1. So starting off with the same property that when they're all added together, we're going to get 1, and then we're going to plug in what we know. So they're all 0.1 except probability of E3 we're trying to find. So we have the probability of E3 plus 0.4 equals 1. When we subtract 0.4 from each side, we're going to end up with 1 minus 0.4 is 0.6. So the probability of E3 is 0.6. Okay. Question 2. What type of diagram is this called? This is a Venn diagram. Suppose the sample points are equally likely. We're going to want to find the probability of A and the probability of B. So this circle on the left-hand side is event A. The circle on the right-hand side is event B. And this whole square is our sample space, S. Okay, so here our key phrase is that the sample points are equally likely. So remember, if our sample points are equally likely, if we scroll up to this property here, so when the sample space is finite and each of the outcomes in a random experiment is equally likely to occur, which is our situation, we define the probability of event A as the number of outcomes in A, or the number of sample points in event A, divided by the total number of sample points. So here we have a total of 10 sample points. So if they're equally likely to occur, the probability of, let's say, 1 occurring would be 1 out of 10, or the probability of 2 occurring would be 1 out of 10, and so on and so forth. So the probability of each individual point occurring is 1 out of 10, using the property I showed you before, because they're equally likely. So now we have to find the probability of event A and the probability of event B. So first, the probability of A, we have sample points 4, 5, and 6. So we would do the probability of 4 plus the probability of 5 plus the probability of 6. So here it would be 1/10 plus 1/10 plus 1/10, because they're all equally likely. So this would be 3/10. And now for the probability of B, we have 6 and 0.7 we have 6 and 7 in event B. So the probability of 6 is 1/10. The probability of 7 is 1/10. So we get 2/10 for probability of event B. All right. Suppose the probability of 1 plus the probability of 2 plus the probability of 3 plus the probability of 4 plus the probability of 1 and the probability of 2 and the probability of 3, they all equal each other to the probability of 5 is 1/20, and the probability of 6, the probability of 7, the probability of 8, the probability of 9, the probability of 10 is 3/20. Now we want to find the probability of A and B. So we're going to do the same method, except our probabilities in this problem changed. So here we have the probability of 4 is 1/20, probability of 5 is 1/20, and the probability of 6 is 3/20. So you add those together, you get 5/20. And then for the probability of B, we're going to do 3 over 20 plus the probability of 7, which is 3 over 20, and we get 6 over 20. All right, question 3. The outcomes of two variables are low, medium, high, and on, off, respectively. An experiment is conducted in which the outcomes of each of the two variables are observed. The probabilities associated with each of the 6 possible outcome pairs are given in the accompanying two-way table. So here we have each column here is low, medium, or high, and then with the first row is on, the second row is off. So here we have our different events defined. So event A would be on, event B would be medium or on, event C is off and low, and event D is high. So now we want to find the probability of event A. So the probability of A is the probability on, and then the probability of on, so when we're calculating that, it's you would add up the values in the first row, because all of these values are when the variable is on. So we have 0.5 plus 0.1 plus 0.05, and we'll get 0.65. Next, we want to find the probability of B, C, D, and A complement. So first, the probability of B is the probability of medium or on. So medium or on, we know or is a union. So this equals the probability of medium union on, which equals, we know that the probability of a union is like the probability of medium plus the probability of on minus the intersection of median and on. So when we're solving this, we're going to have, so the probability of median is, so this column here, this middle column is the medium column. So we're going to want to add up the values in that are associated with medians. So we have medium. So we have 0.1 plus 0.07. So we get 0.17. And then the probability of on, which we calculated in part A, is 0.65, which is the values in the first row added. And then we subtract the intersection, which the intersection of medium and on is 0.1. So here I would trace my finger down, and then I would trace my left finger from on, and then I would find that value. That's how I do it when I'm working it out, because it's easy to kind of choose the wrong number if you're not tracing carefully. So I always have like my right hand trace the columns and my left hand trace the rows. Anyways, so the intersection of medium and on is 0.1. So when you add these and subtract 0.1, you get 0.72. And then we need to find the probability of event C, which is off and low. So remember, and is our intersection. So the probability of off intersect low would be, so if I'm, following, okay, we're in an off situation, and then we need to find our low, which is this first column. We have 0.25 as our answer. And then we want to find probability of D. So D, we were given that event is high. So the probability of high equals, so let's look at where high is. So it's this last column here. So we're going to add up 0.05 plus 0.03, and we get 0.08. And then lastly, we need to calculate the probability of A complement. So there's two ways to do this. So first, the probability of A complement equals 1 minus the probability of A. And a way to remember this is, so if you remember that the probability of our total sample space S is always going to be 1, A complement would be everything in our sample space, but not A. So that's why if you think of 1 minusing the probability of A, that would give us our A complement. So that's just a way to remember it. So anyways, so our probability of on is 0.65 because you would just add this first row. So 1 minus that is 0.35. Okay, another way to think about it is, so the probability of A complement is the probability that we're not on. So that would mean that we're, that would be the probability that we're off, because these are mutually exclusive events. You can't be on and off at the same time. So the probability of off would be 0.25 plus 0.07 plus 0.03. So if we add those together, we also get 0.35. So whichever way you think, which makes sense to you, go ahead and do it that way. But usually people gravitate towards this because if you accidentally, choose something that's not mutually exclusive, you might get yourself into trouble. So this is the better way to think about it. But I did want to show both ways because sometimes there's more than one way to get to the final answer. Okay. Problem C is find the probability of A intersect B. Sorry, not intersect, union, A union B. So that would be, so if we look at what is event A? A is on and B is medium or on. So we would have the probability of on union, the probability of medium or on. So that means we have, the probability of on, union, medium, union, on. And then I can kind of disregard these ons because that's like redundant information. On with union, on is on. So anyways, we're going to have probability of on, union, medium, which is, we already found, which is the probability of B, which is 0.72. Okay, and then find the probability of A intersect C would be the probability of on intersect off and low. So here, I can look at this intersection first, and then and is an intersection as well. But notice that something cannot be on and off at the same time. So this is disjoint or mutually exclusive events. So that would be an empty set because there's no points that would be in the on event and also the off event at the same time. So then an empty set intersected with the empty set, well, there's going to be nothing in common in both these sets. So we're going to have an empty set again. And if you're trying to find the property, we would have, where is it? Oh yeah, here, mutually exclusive events are disjoint. So that's here in our list of properties in case if you couldn't find it. So here, off intersect with on is the empty set. Okay. Where are we? All right, now we're on to question 4. So when they were first produced in 1940, M&M's plain chocolate candies came in only a brown color. Today, M&M's in standard bags come in 6 colors: brown, yellow, red, blue, orange, and green. According to Mars Corporation, today 24% of all M&Ms produced are blue, 20% are orange, 16% are green, 14% are yellow, 13% are brown, and 13% are red. Suppose you purchase a randomly selected bag of M&Ms, plain chocolate candies, and randomly select one of the M&Ms from the bag. The color of the selected M&M is of interest. Identify the outcomes sample points of this experiment. So if you randomly select one M&M from the bag, our outcomes would be, our different outcomes would be the different colors, whether we choose a brown M&M or a yellow M&M, because the color is what's of interest. So our different outcomes would be brown, yellow, red, blue, orange, and green, which are all of the colors that are listed here. So next we're going to assign probabilities to the outcomes in A. So here we're given all of our probabilities. So the probability of brown we were given as 13%. The probability of red is 13%. The probability of orange, which is O, is 20%. The probability of yellow is 14%. The probability of blue is, where is it? Oh yeah, 24%. And the probability of green is 16%. So 0.16. What is the probability that the selected M&M is brown? So we just said that the probability of brown, or the probability of B, is 0.13. In 1960, the colors red, green, and yellow were added to brown M&Ms. What was the probability that the selected M&M is either red, yellow, or green? So notice here that we have an OR situation. So we're just going to add up all the probabilities together. So we're going to have 0.13 plus 0.16 plus 0.14, which gives us 0.43. In 1995, based on voting by American consumers, blue was added to the M&M mix. What is the probability that the selected M&M is not blue? Okay, so now we're going to be interested in blue complement. So the probability of not blue is the probability of blue complement, which is 1 minus the probability of blue, which equals 1 minus 0.24, which is 0.76. So that is the probability that the selected M&M is not blue. And then if you wanted to solve it the other way, you could also go here and add up all of the probabilities except the blue. So 0.13 plus 0.13 plus 0.2 plus 0.14 plus 0.16, and you should get the same answer of 0.76. So whichever way you think about it, this is obviously the more efficient way to calculate that. So this would be good to be your default. All right, so question 5, guilt in decision making. Refer to the Journal of Behavior Decision Making, January 2007 study of the effect of guilt emotion on how a decision maker focuses on a problem. Exercise 3.48. Okay. The results, number responding in each category for the 171 study participants, are reproduced in the table below. Suppose one of the 171 participants is selected at random. So another way to visualize this is, let's say we put all of the participants, in a, like their names or whatever, in a bag, and shuffle it up. So we have 171 names in a bag. And then if it's selected at random, you're going to, randomly choose one name out of that bag or out of the hat. And so here we have guilt, anger, neutral, and then our columns are choose stated option, do not choose stated option. And then here our last column and our last rows are just our totals. So yeah, the numbers added up. And then here you'll notice that our overall total is 171 participants in this lower right-hand corner. Okay, so given that the respondent is assigned to the guilty state, what is the probability that the respondent chooses the stated option? So here, just for my purposes of showing my work, I'm saying that event A is the choose stated option and B is do not choose stated option. So that's just how I'm going to refer to them when I'm doing my work below. So here we want the probability the respondent chooses the stated option. So that's A, given the respondent is assigned to guilty state. So we want the probability of A given guilt. So here, that equals the probability of A intersect guilt divided by the probability of guilt. So this first, how I got this was one of the properties written above. So, so then to compute this part, so let's just look at the numerator first. So, excuse me, the probability of A intersect guilt would be, okay, so we're in the A column, and then we need to look at, okay, the guilt row. So here we have 45. And then we're going to divide it by the probability of guilt. So the probability of guilt would be the total row of guilt. So that would be 57. So our answer would be 45 divided by 57. Okay, part B, if the respondent does not choose to repair the car, what is the probability that the respondent is in the anger state? So here, do not choose stated option means the choose not to repair the car. So, so this, we're given that, what is the probability that the respondent is in the anger state? So that's a probability of anger, given B. So, this is the same property as before. So we can do probability of anger intersect B divided by the probability of B. So if we look at that, so first probability of, so we're in the B column and then we want to find anger, follow that across. So we get 50 as in our numerator, and then the probability of B, so our total for the B column is 111. So 50 divided by 111. So now we want to know, are the events repair the car and guilty state independent? So to find if something is independent, or to show if something is independent, you can do the probability of A intersect. Let's say we have two events, A and D. So if we want to show that A is independent of D, we would do the probability of A intersect D, would be equivalent to the probability of A times the probability of D. So here we're going to do just that. So let's say if event A is repair the car, and then event D, I just named that guilty state is D. And this is A, which is the column that I named above. So first let's find the probability of A and the probability of D alone. So the probability of A repair the car would be 60 out of our total, which is 171. And then the probability of D guilt, which is guilty state. We're going to look here. Guilt is 57 out of our total, which is 171. So 57 divided by 171. Okay, and then we want to find, okay, what is the intersection of A and D. So the probability of A and D. So the probability of A and D, which D was anger, right? Yeah. No, guilty, sorry. So guilty, so that would be 45 because we're in column A, and then guilt 45 out of our total, which is 171. And all right, so that is our intersection. So the probability of A and D is 45 over 171. And now let's see if that equals the probability of A times the probability of D. So if I multiply these together, we're going to get 20 over 171. So that obviously does not equal 45 over 171. So that means that these events are not independent. If we got the same answer, like if this was 45 over 171, let's say, then we would say they're independent. But because we didn't get the same answer, they're not independent. Okay, question 6. Study of why EMS workers leave the job. Refer to the Journal of Allied Health, study of why emergency medical service EMS workers leave the profession. Recall that in a sample of 244 former EMS workers, 127 were fully compensated while on the job, 45 were partially compensated, and 72 had non-compensated volunteer positions. Also, the numbers of EMS workers who left because of retirement were 7 for fully compensated workers, 11 for partially compensated workers, and 10 for non-compensated workers. Given the former EMS worker was fully compensated while on the job, estimate the probability that the worker left the EMS profession due to retirement. So here we have a keyword given, so I'm going to think to myself, it's probably going to be a conditional probability because we're given information. So we want to estimate the probability the worker left the profession due to retirement. So that's the probability of retirement, given that the former EMS worker was fully compensated while on the job. So we have probability of retirement given fully compensated. So here we have, so if we look for retirement, where is that? Sorry. Okay, so we have 7. We have 7 were left because of retirement and were fully compensated. So that would be 7 over 244. And we're going to divide that. And here we got 244 because the total sample size is 244. And then we're going to divide that by, okay, given fully compensated. So we have 127 were fully compensated. So 127 over the total, which is 244. So when you take this fraction divided by this fraction, you get 7 over 127. Given that the former EMS worker had a non-compensated volunteer position, estimate the probability that the worker left the EMS profession due to retirement. So here we're going to have another conditional probability because, we have that keyword given. So we're going to find the probability of retirement. Yeah, because they left EMS due to retirement, given non-compensated. So here, if we scroll back up, we have that 10 left because of retirement and were non-compensated. So 10 over 244 is going to be our numerator, and then divide that by, okay, non-compensated. So if I look here, non-compensated 72, so 72 divided by 244. So the top fraction divided by the bottom fraction is 10/72. Are the events a former EMS worker was fully compensated on the job, and a former EMS worker left on the job due to retirement independent, explain. So here we have, I'm just going to say that this first event is A, and the second event is B in my work. Well, actually, no, I didn't end up, well, okay. So we'll probably want to use this property that if A and B are independent, so if they're independent, then that implies that the probability of A given B equals the probability of A. And a way to remember this is they'd be independent. If this holds, they would be independent because knowing information about event B wouldn't change the probability of event A. So that's a way to remember it. All right, so going back to this problem. So the probability of retirement given fully compensated is 7/127. That's what we found in part A. And then the probability of retirement would be 7. So I'm going to add up all these three numbers down here. So the numbers of EMS workers who left because of retirement, which is 7 plus 11 plus 10. So that would be our numerator, which is 28, and then divided by the total, 244. So here, 7/127 does not equal 28/244. So they're not independent. If they were equal, then yeah, they would be independent. But since they're not equal, they're not independent. Okay. Question 7, maybe I should go like this. Okay, suppose the events B1, B2, and B3 are mutually exclusive and complementary events such that the probability of B1 equals 0.2, the probability of B2 equals 0.15, the probability of B3 equals 0.65. Consider another event A such that the probability of A given B1 equals 0.4, the probability of A given B2 equals 0.25, and the probability of A given B3 is 0.6. So now we're going to use our Bayes rule to find, so first this probability of B1 given A. So let me just scroll up to show you where Bayes rule was as you're following along in yours, sorry for the amount of scrolling. Okay, here is where our Bayes rule is. So we're going to essentially be solving, this bottom fraction here. All right. It'll be faster if I just go like that. All right, so the probability of B1 given A equals the probability of B1 times the probability of A given B1 divided by the probability of BI times the probability of A given BI. And we're going to do the summation of that from I equal 1 to 3. So if we unpack the denominator, we're going to get this thing, which I know looks scary, but it's not that bad. So here we would just, since here we have a total of, our I goes from 1 to 3, we would have the probability of B1 times the probability of A given B1, and then add that to the probability of B2 times the probability of A given B2, and then add that to the probability of B3 times the probability of A given B3. So, all right, so if we plug in what we know and solve, so the probability of B1 equals 0.2. The probability of A given B1 is 0.4, which is, right here. Then the probability, and then we're going to divide that by this scary looking denominator, but I promise you it's not that scary. So we have the probability of B1, which is 0.2 times the probability of A given B1, which is 0.4. And then we're going to add that to the probability of B2, which is 0.15, times the probability of A given B2, which is 0.25. So that's here. And then we're going to add the probability of B3, which is 0.65, times the probability of A given B3, which is 0.6. So that's here. So when you put this in your calculator, you should get 0.08 divided by 0.5075, which is 0.157635. So that is, yeah, so we just used the Bayes rule to find that. So here, to find the probability of B2 given A, it's going to be similar, but here our numerator changes because now we're dealing with B2. So the probability of B2 times the probability of A given B2. But our denominator is going to stay the same as above. So when you, so this will be the same as above, the denominator. And then our numerator is going to be the probability of B2, which is 0.15 times the probability of A given B2, which is 0.25. So you're gonna get this fraction, the 0.0375 divided by 0.5075, which equals 0.073892. Okay, and then the last one is the probability of B3 given A. So here you'll notice that our denominator is staying the same as before, but our numerator changes because now we're doing B3. So the probability of B3 times the probability of A given B3. And then that would be 0.65 times 0.6 divided by that long denominator, which simplifies to 0.39 divided by 0.5075, which equals 0.768473. So I just used my calculator to solve this. And if you notice, I don't know if this will help you solve them, but so like here, the probability of B1 given A, so notice that like this numerator here is where is it? Where was I? Well, maybe it's easier to show here. Probability of, like, for example, like this numerator here, the probability of B3 times the probability of A given B3 is this chunk of the denominator, like the last thing added. So here, like the 0.65 times 0.06. And then for the second one would be the middle chunk of the denominator, which is the 0.15 times the 0.25. And then this first one here is like the first chunk of the denominator, the 0.24. So when I'm going through, and you know, when I had to solve all three, I don't know, it just helped to realize that when I was plugging things into my calculator. Anyways, so that concludes recitation 5 for stat 315, and I hope that helps.